Okay, our third form of proof. We've dealt with direct proofs, we've dealt with proof by the contrapositive. We're now going to deal with proof by contradiction. This is on page 218 of your book. Okay, so there might be statements which really, before we read what they've written, we use the proof by contradiction when statements can be rephrased as implications. That's mainly where we're going to use this. Okay, so there might be statements which really cannot be rephrased as implications. For example, root 2 is irrational. In this case, it is hard to know where to start. What can we assume? Well, say we want to prove the statement P. What if we could prove that if not P, then Q, where Q was false? If this implication is true and Q is false, what can we say about not P? It must be false as well, which therefore makes it a truth for P. This is how the proof by contradiction works. If we can prove that not P leads to a contradiction, then the only conclusion is that not P is false, so P is true. Okay, that's what we wanted to prove. In other words, if it's impossible for P to be false, then P must be true. Okay, so this is the structure of our proof. We're going to prove that if not P, then Q, where Q is false. If this is true, and Q is indeed false, then not P must be false as well. Therefore, P is true. Okay, you can see exactly how the negation fits in here. Okay, so let's look at one of the most famous proofs, and that is the proof that the root of 2 is indeed irrational. We're going to prove that by contradiction. Okay, so let's look at the proof that shows that root 2 is irrational. Okay, so we're going to prove this by contradiction. So we're going to suppose that root 2 is not irrational. Now what does that mean? It means, therefore, root 2 can be written in the form a over b. Now remember, where a is an integer and b is an integer. Okay, so a and b are both chosen as integers. So the root of 2 can be written in that form because we're supposing it's not irrational. Not irrational makes it rational. Okay, so if I look at the root of 2 and I want to equate it to a over b, if I square both sides, I get 2 is equal to a squared over b squared, which then brings me to a statement that a squared is 2b squared. Okay, so that is the case if we have root 2 as rational. But now remember, we have to state here that a over b is in simplest form. Folks, now that means that there's no common factors between these two. So as an example would be 2 over 3. 4 over 6 will not be in simplest form because we can still remove a 2 that's common. So we're assuming that it can be written in that form where a over b is written in its simplest form. Okay, so what does this mean? A squared equal to 2b squared tells us that a squared is even. Why? Since b squared is an integer. Okay, and because b squared is an integer, it's a multiple of 2. So a squared is definitely then an even number. Now that implies, we've seen earlier, that a is even. Now what does that mean? That means that we can write a as a multiple of 2, where k is any integer that we can think of, some integer. Okay, now what does this mean? This means that a squared can then be written as 4k squared. Now if you look carefully, we've got a statement here about a squared and we've got a statement here about a squared. So if we equate those two, then we get 2b squared is equal to 4k squared, which then comes to be b squared being 2k squared, which again is even, since k squared is some number that is integer. Now folks, what does that mean? This means that in our case that we've got over here, b is thus even. Now if a is even, okay, and b is even, then, but this means that a over b is not in simplest form. Why? Because we can write b as a multiple of 2 and we can write a as a multiple of 2. So there's definitely a common factor between the two of them. Okay, so what is this? This is a contradiction. Why is it a contradiction? Because we said in the beginning a over b must be in simplest form. Therefore, the root of 2 is indeed irrational. Okay, proven by contradiction. Okay, let's look at the next proof I want to discuss with you. This one says, prove there are no integers x and y such that x squared is equal to 4y plus 2. Now we're going to do this by contradiction again. So we're going to assume, or we're going to suppose there are integers x and y such that x squared is equal to 4y plus 2. Okay, now let's see what can we do with that. If we start looking at x squared, which is equal to 4y plus 2, then what do we have? What can we do rather? We can remove a 2 and we'll be left with 2y plus 1. So what does that tell us about x squared in this case? Again, we have seen this before. Therefore, x squared is even, since 2y plus 1 is an integer for some value of y, that is integer. Okay, so this is even, that makes x squared, that makes x even as well. Okay, so that's what we can conclude over here. After x squared was even, we can definitely say x is even. Okay, now with x even, what can we say? We can say that x can be written as 2k, where k is some integer, so x can be seen as a multiple of 2. Okay, so let's see what that has, what this implies. Well, if I form x squared again, I form 4k squared, and I now have two statements for x squared again. I've got the statement A up there, I've got the statement B down here. Now if I equate the two, I get that 4k squared is therefore equal to 2 times 2y plus 1. If I divide both sides by 2, I get 2k squared, which is equal to 2y plus 1. Now this is a contradiction, which is a contradiction. Why? Because here 2k squared is even for k some integer, and here 2y plus 1 is odd for some integer, or for any integer actually, not just some integer, any integer y. And this we cannot have. An even number can never equal an odd number. Why is this even? Because it's a multiple of 2. All multiples of 2 are even numbers. This here is a multiple of 2 plus 1. Therefore it's odd. So even can never equal odd. Okay? Therefore, there must... Well, what was the original statement? It said, prove there are no integers, x and y, for which that's true. Okay? So there must not be integers, x and y, for which we can say that x squared is equal to 4y plus 2. Proven by contradiction. So you can see how your proof by contradiction works. It's really not that difficult. Okay folks, our next example is example 329. It's on the pigeonhole principle. Now what does the pigeonhole principle say? It says, if more than n pigeons fly into n pigeonholes, then at least one pigeonhole will contain at least 2 pigeons. And it asks us to prove it. Okay, so let's see how that works. Well, here's your proof. It says, suppose, contrary to the stipulation, that each of the pigeonholes contain at most 1 pigeon, then at most there must be n pigeonhole or pigeons. But we assumed that there are more than n pigeons. So this is impossible. There's a contradiction here. Thus, there must be a pigeonhole with more than 1 pigeon in it. There must be at least 1 pigeonhole that has more than 1 pigeon in it. And that's the pigeonhole principle.